Good morning, everyone. My name is Léo Brechet, and I'm currently in PhD. But the two past years, I worked on the ONE-PIX. The first year, I was in internship in Angers, and I compared it with a standard hyperspectral imager named HiSpecs Vinair 1600. And the past year, I worked with Arvalis and the agrophotonic team in Lannion to improve the accessibility for technicians, experimental technicians, uh, with the ONE-PIX. Um, so my work was mainly about uh, um, driving a data measurement campaign, sort the data and save them, and also, of course, improve the GUI, so the graphical user interface of the ONE-PIX, so that it's easier and more accessible. So to give a little bit of context, here we can see all of the setup of an epidemic surveillance network in Arvalis. So the technicians uh, take samples at the field directly, and then they quantify the symptoms on the plants, and also they identify them. And when it's difficult to say to determine the nature of the pathogen, they do board for validation, which are then sent to a genetic laboratory. And our proposition here is to gather data, a large amount of labelized data using this board with the ONE-PIX directly to build a database of spectral signature, and also to help the technicians during the quantification phase by estimate the symptoms area. So now we'll be talking about the ONE-PIX. So it's composed by this five main components. So first, the computer that drives everything is a Raspberry Pi 4 Model B. We also can see a video projector that can send structured light on the scene. There is an RGB camera to provide another modality for smart scanning, which I will mention later. Then we can see the collector that receive light and drive it directly into the fiber spectrometer that provides hyperspectral images. There is two types of acquisition. The first one is called full measurement. And as Nicolas said, we use a set of patterns to rebuild the image through an intermediate mathematical space. Here we can see that the image is reconstructed through the FFT space, so the discrete Fourier transform space. This setup has few advantages and also a drawback. So first, the resolution is fully customizable in the limits of the video projector resolution, of course. It is also possible to choose the projection base. So here it is the Fourier base, but you can choose, for example, the Hadamard base or all base you want. And it is ideal for education approaches because it is real transparent, and you can see what's going on in live. I can say so. It has also, like I say, some drawback. For example, the time of the acquisition can be very long. For example, for a 31 by 31 image, we can count around 5 or 6 minutes. But if you want a way more resolution, for example, 81 pixels, it's around 1 hour. Also, there is errors during the reconstruction process. And from now, when I will be talking about this method, you will see this picture in the top right hand corner. The second method is the addressed measurement. So it's basically smart scanning measurement. We can see on the animation, the first step is to adapt the field of view of the RGB cam and the spectrometer. Then we can use this RGB picture to segmentate the image and then project light only on the region of interest, like we can see here, so that in the end, the spectrometer measure one mean spectrum for each region of interest. So as we can see, it is very fast, and the sample is much less exposed to the light. So it is also less destructive for the samples, and mainly the biological samples, and it's less energy consuming. Of course, because it's a mean spectra, it is less noisy spectra, and yes, because the regions that are measured are bigger than just 1 pixel. The problem of this method is that the quality of the segmentation defines the quality of the hyperspectral image. So it is impossible to roll back the process to improve the quality of the measure. Also, the field of view of the RGB cam and the spectrometer are hard to register very accurately. And when I will be talking about this process, you will see this picture. Now let's talk about the GUI that are implemented to use this method. So the first one for the full acquisition is a 3-tab GUI. The first one is for the acquisition. So you can set up the resolution, the integration time, and also choose the pattern you want to use. You see here, sorry, here it's Fourier base, but you can also use Adamar and so on. The second tab is for a quick analysis, so for the hypercubes. So we can, for example, trim spectra and draw a spectrum of the selected pixels, and also perform some clusterization. And the third one is the one that I made, and it's useful to explore quickly the different indices, spectral indices that are mostly used to see a phenomenon that you're searching for. Okay. Then we have the second interface, so for the addressed acquisition, and it's a very simple GUI. You just have several buttons, and You just have to click here to initiate the process, and then just clicking here, you get an image. And we'll talk about it a bit more later. So now we described all of this, we can talk about the measurement campaign itself. To begin, I, I'll be talking about the different setup that I use. So here in the left, you can see the lab setup made of aluminum profiles, but quickly we change this material to the wooden support you can see here, because it's more accessible, it's less expensive, and all of that provides a better accessibility to the support, and it's easier to deploy. This setup is easily printable using the plans you can see here, which are also in the GitHub of ONE-PIX. Now that I introduced that, I can describe the simple procedure that we created to acquire our data. So first, we are preparing scenes. Then we start up we're starting up the ONE-PIX. We ideally we calibrate the measurement thanks to a calibration carpet that you can see here. We then begin the acquisition, and in the end we get in one hand the masks with different labelized areas, which is useful to help quantification. And in the other hand, we have labelized the data, labelized the spectral labelized spectral data, which can be useful to train a presymptomatic identification model. Our data are separated in two types. So in the left hand, you can see the full plant data. So here we just put the plant on a background and acquire the data. And on the right hand, you can see sort of board like the identification board I told about before. And our data set is composed of gray, white, and black background. During this campaign, we also use the experience of the user to improve some points. It is very useful to role play with technicians because it provides a better accuracy on the point which need to be fixed or improved. For example, it's by this process, by talking with technicians, that I came with the idea of this simple GUI, which which a few buttons, so that the technician doesn't have a long time to learn before process the acquisitions. And also, I came with the idea to group the two acquisition in one single home GUI, which you can see here. It also provides a translation so that the technicians are able to work in their own languages. These translations are provided by a simple JSON dictionary, so it's easy to add some languages. And that's it. And also, like I said before, I had to sort the data and backup them. So I realized a CSV like it's often made, which list all the acquisition parameters, which will be then useful to process statistics model, to train a different model, and to do statistics on them. Here we have an example of N0 results, so raw data, using full uh, the full acquisition method. So you can see here the spectrum of this very pixel, and it is very noisy because it's only 1 pixel. Very it's a very little area on the images. Then I try to normalize the data very roughly, as you can see here. So there is a lot of aberration. The dark current isn't corrected here, but the idea was to judge the middle value, so between 400 and 700. Uh, and also, this process wasn't the main purpose of my internship. And finally, we have the N2 results. So here we take the image and we do 2 masks, and we pretty much do as it is an addressed measurement, if I can say so. So we do a mask corresponding to chlorosis, which is the yellow part of the plants, and we do a mask with the healthy part, so the green part, and we plot a mean spectrum for each. And here I choose this image because we used it to see immediately that there was a problem of saturation, just as you can see here. And I wanted to say that it was fixed immediately, so we don't have this problem anymore. To continue, we have the data of the addressed method. So here we can see some mask which corresponding to the same color spectrum here. And here the N1 data or the final data, because you just have to normalize them to get a mean normalized spectra. And also here we got a little bit of saturation, which also have been corrected. So this internship has allowed to improve the GUI of the ONE-PIX in terms of accessibility and quality of life, but it also highlights what comes next. So, for example, we need to improve, I needed to improve the quality, the metrological quality of normalization, and guarantee the repeatability of the measurements. And also, it is possible to think of a tool that guarantee an automatical data backup, because here the CSV has been made only manually during all the campaign. But actually, yet the setup makes it possible to collect a large amount of low-cost label data, which can be used then to feed detection models, because everyone occurred to say today the real bottleneck of the pre-symptomatic symptoms detection and identification is the lack of data. And in the end, ultimately, the goal is to build the ultimate sensor, if I can say so, that would be able to make measurements and to identify the diseases directly at field.